Yeah, hello everyone. Today we have Jayadev and he'll be presenting a tour on optimization methods. Yeah, you can start.
Yeah, my name is Jayadev. I'll be talking about optimization methods. I'll be giving an overview on unconstrained minimization. Specifically in this, I'll be talking about line search methods. Yeah. So what exactly is an optimization method? So if you go to a textbook, this is the basic definition that you'll find. So there is a objective function. Here in my case, I'm just going to consider the Euclidean space Rn, and the cost function is just going to be a real valued function. So objective function from Rn to R, and then we have a set of constraint functions on the same domain and range, which we call as constraint functions. So our problem is basically to minimize this objective function over some set subject to these set of constraints. We have inequality constraints and also equality constraints. And what about this set? This set can be, it is usually the intersection of domains of all these functions. It can also be a smaller set than this or something like that. So given this problem, our main attention is to solve the optimization problem, that is to find a minimizer for this objective function which satisfies all the constraints. So for this talk, I'm focusing on the unconstrained optimization problems, where we just say our x is any point in the Rn, and we want to minimize it. We want to minimize an objective function over whole of Rn, where we usually have some additional conditions on the function. Yeah. So some more basic terminology. So what are the type of minimizers? So the solution, what kind of solutions can we expect? So one best solution that we can find is the global minimizer. So it is a point in the domain, or in our case, it's just Rn. It's called global minimizer if the function value at that point is the minimum for all the points for all, the points in the whole domain. If that is the case, then we call it global minimizer. And the local minimizer, in this case, we say it is a minimizer only in a local neighborhood of this point. So here, if you are not very clear with what neighborhood means, it is a topological concept. For now, it will suffice to just take it as a what should I say? Uh, Open sphere about x naught, and in that open sphere, for every point, this condition is satisfied. So it is then called as a local minimizer. And then we also have a concept of strict local minimizer, where we want the inequality to be strict, and also only one point should be satisfying this inequality. So if that exists, then we call it as strict local minimizer. So yeah, and also we also need to know a little about the rate of convergence. So let's say we have a sequence xk in Rn, and say it converges to xk. So it converges to xk as limit k tends to infinity, xk tends to xk is the limit is equal to x star. So in this case, we can talk about rate of convergence, like how fast the sequence is converging to x star. So we have three simple notions of convergence, rate of convergence. The first is Q linear convergence. So here the Q will mean quotient. That is, we take quotients of some quantities to quantify the rate of convergence in each case. So here we say a sequence converges Q linearly to x star if there is a constant between 0 to 1 open interval, such that this quotient, the quotient corresponding to the k plus 1 term and the kth term, if this is less than or equal to r for all sufficiently large k. So if this condition is satisfied, then we say the sequence converges to x star q linearly. And here, this is some notion of convergence. We have a faster notion of convergence, where we want the limit as k tends to infinity of this ratio to be equal to 0. So it is, in a sense, like if you try to analyze these two things, here this can be any point between 0 to 1, any number between 0 to 1. And here, as limit k tends to 0, infinity, we do not strictly want it, we do not strictly need it to go to 0. But when it does, it's called Q superlinear convergence, and it's a little faster than linear convergence. And then we have the fastest, at least the optimization algorithms. These are the best things that one can expect. And this Q quadratic convergence is basically if there is a positive number constant m, which doesn't necessarily have to be less than 1, such that this condition is hold. This condition holds for all sufficiently large k. So basically, these are the three like notions of rates of convergence of sequences. So here, xk can be anything. Like they can be a set of vectors, in which case we will have some notion of norm here, distance between 2 points, or they can also be any numbers, say errors or anything. Yeah. So if you want, these are three examples. So this converges Q linearly to 1, and this converges Q superlinearly to 1, and this converges Q quadratically to 1. You can verify that later. Yeah. So now we want to like have the basic tool set. Like our optimization algorithm, like we do not directly want to solve them. Like in one step, we may not be able to solve because the function might be very complex. So we want to solve the optimization problem iteratively. As in, at each iteration, we have a estimate of a solution, and as the iterations progress, we want the estimate to get better. So in this way, basically, we are updating our solution. So we want to have a notion of identifying, like when we come across a, minimizer or like local minimizer or global minimizer, how do we actually identify that? Like we only have the knowledge of the function values at some points. Like whatever points we have traversed, only at those points we will have the function value. So with that knowledge, how do you actually identify that a point is a local minimizer or a global minimizer? So these are some tools from the calculus that we will need. So the first thing is the first order necessary condition. So what this says is if x star is a local minimizer and if f is continuously differentiable, that is the derivative of f is continuous, then if that holds in a neighborhood of x star, then grad of f of x star is equal to 0. So essentially, like what this implies is if x star is a local minimizer and f satisfies this condition, then this condition holds. It's not the other way around. That is why it's called necessary condition. And because we need the first order derivative, we say it's first order necessary condition. Yeah, that is one thing. So the other way around, if you look at, so from the above condition, notice that every local minimizer is a stationary point. Like we define stationary points to be the points where gradient vanishes. So from this condition, what we can say is every local minimizer is a stationary point of the function. That is one note. And then we have the second order necessary condition where like we assume second order gradients existing and what conditions will hold for the function at that point. So if x star is a local minimizer and if Hessian of f is continuous in an open neighborhood of x star, then grad f of x star is equal to 0 and Hessian at that point, it will be a matrix. This matrix will be positive semi-definite. So positive semi-definite is a matrix whose all eigenvalues are non-negative. It can also be 0, but they are non-negative. They should not be negative. So this is the second order condition. So essentially, if x star is a local minimizer, then second order condition says these two conditions, these two properties will hold. Yeah. And then we have second order sufficient condition. So basically, so far, these two conditions, if you see, a local minimizer will satisfy these conditions, but it's not necessary that if these conditions are satisfied, then that point is a local minimizer. So here we actually have a sufficient condition, but we need second order requirements of the function. So suppose that grad f bar, like Hessian of f, is continuous in an open neighborhood of x star, and that grad f of x star is equal to 0, and Hessian at that point is positive definite. So here it's positive semi-definite, and here it's positive definite. If these conditions hold, then that point that we are concerned about, this particular point is strict local minimizer. It's not just local minimizer, but it's also strict. So this is one like good thing to have. So basically, we can tell for sure if we encounter a point where these two conditions are satisfied, and we can also prove that it is continuous in an open neighborhood of this point, then we can for sure tell that that point is a strict local minimizer. So yeah, this is a second order sufficient condition. And then now if we have convexity in our picture, it's better. So when f is convex, any local minimizer x star is a global minimizer of f. This is a very good condition, very good property of a convex function. But usually, there are many convex functions, and usually people solve the optimization problems by converting them into convex equivalents. But still, this is not the only way we can solve. There are also better. Sometimes it's better not to just convexify and just solve the direct problem. Probably you might get to a good solution, good enough solution, so something like that. But yeah, this is one thing that one can note is when we have a convex function, then any local minimizer x star is a global minimizer. And if in addition we have the differentiability condition, here we do not need the differentiability condition, but in addition we have the differentiability condition, then what we can tell is any stationary point x star is itself a global minimizer. So this is much better. So yeah, these are basically the techniques, tools from the calculus that we'll be using to identify the minimizers. Okay. So now, what should be the goal of an optimization method? So given an initial point, iteratively find a sequence xn at each step such that as the limit tends to infinity, as the iterations progress, some of the above mentioned conditions of optimality are satisfied. That is, it might not be the global minimizer, but at least some of them is satisfied. And we should be able to prove it for a wide variety of functions, not just saying for one particular function, if this is satisfying, then it's not a very good method. It should generalize to a wide variety of functions. So basically, we want to look at those optimization methods which can generalize to a quite a lot set of functions. Yeah. So this is our goal. We want to have a method such that at the limit, some of the optimality conditions are satisfied. Okay. So there are two broad classes of optimization methods. One is line search methods, and the other is trust-driven methods. Line search method is mostly one example that everyone might have known is the gradient descent. It's a line search method. It's basically we are going to talk about it, so I'll just save it for the rest. I'm not going to talk about trust-driven methods. It's a topic in itself, and it has a lot of theory that is involved. So we might save it for a next talk. Here, what happens is, in contrast to gradient descent, we fix upon a search direction that is the negative of the gradient at a point, and then we want to see how far we want to move in that direction. But in case of trust-driven method, what we do is we actually not just fix upon that, but we want to model the function in a neighborhood of a particular iteration. We want to have a easier solvable problem, solvable optimization problem, which approximates our original problem. So, okay, I'm a little I cannot explain it briefly. So we'll just skip it for now. I'm not going to focus on this. Our main focus from now will be on line search methods. So yeah, so what is a line search method? So this is a prototype of any line search method. A vast variety of line search methods fit into this prototype. So basically the setup is we are given an initial point, and given that initial point, at each step we pick a direction pk, and we also pick a step length alpha k in that direction, which should be positive, and then we update our solution by the step. So we do this iteration until some notion of convergence is reached. Like usually a gradient of the objective function, if it is less than some particular tolerance, then we say yeah, it has converged or something like that. So basically, this is a line search method. So here, if you observe, 1, 3, and 4 are non-trivial. Like this, these two steps, they are definitely non-trivial. But one should actually know that even the first step, picking a point itself, is a non-trivial method, and we'll actually see why it is a non-trivial step. We'll look at it later. So so roughly speaking, here what we want is we want to like the line search method. The goal should be that at each point, whenever we generate a new, whenever we update the solution, it should be in such a way that the function value at the updated solution should be strictly less than f of xk, the current solution. If this is not the case, then as we approach the limit, then there might be cases where it might be completely monotonous. It's neither increasing or it might even be constant. So we do not want cases like that. So we strictly want like methods in such a way that they update the solution in such a way that like we definitely have a decrease in the objective functions value as the iterations progress. So these type of methods are called descent methods. And one quality of this descent method is the direction that we are choosing. First thing is like a basic result from calculus is that minus grad f of xk will be the steepest descent direction. That is the direction at xk which has maximum decrease. The direction in which the maximum decrease is encoded. That is minus grad f of xk is that direction. So we quantify like descent methods by a descent direction, and the descent direction is any direction pk, any vector pk, such that its dot product with grad f of xk will be negative. So it says that it has an acute angle with the steepest descent direction. Then it is called descent direction. So basically, we want to look at descent methods which pick some descent direction and also some step length such that eventually it converges. And the rate of convergence should also be an important factor when we are considering the optimization algorithm. So, yeah. So first, now we will look at these two steps. First we'll see how to pick a step length, what general conditions should be satisfied when picking a step length, and then we will see what type of descent directions should be used. Like it might be very one might be willing to directly take the negative of this itself to be the Wilson direction, but it might not in worst case be very good. So we want to look at some general algorithms where this direction is picked in some other ways, and still we have a convergence notion of convergence. So when we discuss which direction to pick, we basically want some conditions on PK such that eventually convergence is seen. Yeah. So now we'll discuss the conditions of step length. So one given thing, like given a step direction, what we want to do in this step is we want to pick a step length such that there is a decrease in function value, objective function. So one could arguably say that the ideal thing would be the better, and the ideal thing is given this direction, uh, xk plus alpha k pk. Okay, here there should be a k here. I missed it. So xk plus alpha k pk is a ray from x uh, in the direction pk, and as alpha k scales, we move along the ray. So the minimum along this ray should be ideal step length. But usually it turns out that solving this problem itself is again in whole a difficult problem. So we usually want to solve this problem iteratively. Like we do not want to compromise on the step length that we want to choose, but in the same time, we do not want it to run for a very long time. So usually what we do is we compromise for some inexact methods where we try out a sequence of stepped lengths until certain conditions are satisfied, which guarantee optimality. So optimality should be something, a notion which say it's the step length that we are choosing is very close to the ideal step length. Okay, so here, Wolf conditions are one set of conditions which which are inexact criteria for selecting the inexact algorithm for not algorithm. It's criteria for selecting step length. So basically, what this reverse condition says is there are two set of conditions. If your step length satisfies both of them throughout your iterations, like if you pick a alpha k in every iteration, such that these two conditions are satisfied, then optimality will be reached. We'll look at that condition. We'll look at that result later, but let's first focus on what these conditions are. So first define phi of alpha k to be f of xk plus alpha k pk. So this is just the function value along the ray. So this is a function in one dimension. Only alpha k is a variable. So phi of xk is yeah, the function value along the ray, and this is L of alpha k. Define it to be this function L of alpha k. So here, if you see at our variable is alpha k, so xk and pk, and these all things are constant. So this is a constant, and even this is a constant, and alpha k is a scalar. So if you see, this function itself is a linear function whose slope is given by this and whose intercept is given by this. So our slope, if you see, since we are considering we are considering the descent directions, and we take this c to be a positive constant, then this slope, if you see, this is going to be a negative slope. Okay. So what the first condition says, armature condition or the sufficient decreases condition, what it says is the function value at a particular alpha k, whatever we are choosing, it should be less than or equal to the this quantity, or in compact form, phi of alpha k should be less than or equal to L of alpha k. So this condition, if you look at it from a pictorial point of view, what this says is the function value, like the alpha k that we are choosing, it should at least be in such a way that uh, like the slope is less than the first order Taylor expansion. So if you see, this is the first order Taylor expansion of this thing. So it should at least be smaller. The slope should at least be smaller than the not the slope, but the function value. It should at least be below the first order Taylor expansion at this alpha k. So that is what this sufficient decrease condition says. And then we also have this curvature condition, which is a little complicated. What it says is phi prime of alpha k should be greater than or equal to c2 times phi prime of 0. So essentially, this condition, it is a little tricky to understand, but in a just what it tries to say is that this condition prevents from choosing small step lengths. Like it might happen that even though we have a function which satisfies, even though we have step lengths alpha k that satisfy this condition, there might be cases where alpha k is very small. So if alpha k is very small, then it's no point. Like we are just taking very small steps. So then the rate of convergence will be very slow. So to restrict that, this curvature condition will ensure that uh, the alpha k's that we are choosing are not very small. So yeah, these are basically these two conditions collectively are called Wolf conditions, and these are conditions on alpha k. So now, given these conditions, we have this result which says yeah. So which says if f is a function which is continuously differentiable and pk is a descent direction, we need it to be a descent direction at xk, and assume that f is bounded below along this rate. So this is the set of all points which the Wolf condition, like our algorithm which picks step length might be traversing. These are all the points that are. This is the set in which are like step length selection algorithm might be traversing. So our function should first of all be bounded below. If it's not bounded below, then we cannot guarantee the result. Yeah. Then what this condition, what this theorem actually says is, for any given C1 and C2 which satisfy this particular condition, there exists intervals of step lengths satisfying Wolf condition. So here, these conditions might be looking like they are very strict, these two conditions. But this result, what it says is, even for any C1 and C2, there actually exist some intervals such that on the whole interval, this Wolf condition is satisfied. So if you have any step length calculating algorithm, say some naive algorithm would be like backtracking line search. If that satisfies these two conditions, that f is continuously differentiable and pk is a descent direction, and this additional boundedness condition, then there will definitely exist Wolf condition. Sorry, there will definitely exist intervals where Wolf conditions are completely satisfied. So yeah, so this is that. So now we want to see what exactly does Wolf condition ensure us. So now we will come to the descent direction selection. So yeah, our descent direction is pk, and this is the steepest descent direction. Then you know that the cos of angle between these two vectors is given by this quantity. So yeah, then what this result actually tells us that uh, yeah, you have an algorithm in which every iteration updates the solution in this way: xk plus alpha k pk. So basically, yeah, where pk is a descent direction and alpha k satisfies the Wolf condition. Okay, so if this is, you have an optimization method which essentially does this, which picks a step direction which is descent direction, and also the step length which satisfies the Wolf condition. And suppose the f is bounded below on whole of Rn, and f is continuously differentiable on open neighborhood of the level set on which we traverse. Since it's a descent direction, we will only be bothered about the points where our function will be traversing. So our points will essentially be bounded by this level set. So on this level set, we require our function to be continuously differentiable in a open set, yeah, containing this, and where x0 is an initial point. And then we need one additional condition which actually turns out to be a very critical condition for guaranteeing the result. So this additional condition is the Lipschitz continuity of gradient on this open set n. So basically what this Lipschitz continuity says is, uh, if your gradient function grad f is Lipschitz continuous, then there exists a constant L greater than 0 such that yeah, this inequality holds for all the points in your neighborhood. Okay, so this is a very tricky inequality to understand, but this actually turns out to be a very key point that actually ensures optimality. So once we have all these conditions, once we have all these assumptions might be looking a little what should I say? Very strict, but they are not actually strict. Usually, whatever functions we consider, unless if you're considering some matrix completion where you have rank instead or stuff like that. Other than that, those in usual cases, these conditions are satisfied, and when all these are satisfied, what it says is, yeah, series, the series sum will be finite. The sum of this cos square theta grad norm square will be less than infinity. So the series will be finite if and only the sum of the series will be finite if and only if as k tends to infinity, the limit of the kth term as k tends to infinity will be 0. So let me just uh, repeat it. Uh, Basically, these are our line search methods where pk is a steepest descent direction and pk is a descent direction, sorry, and alpha k is a Wolf condition. And in addition, we have these three extra conditions that we require. If these things are satisfied, then we can guarantee that as k tends to infinity, cos square theta k into norm square of grad will be equal to 0. So essentially, we cannot strictly say that the like as this condition is satisfied, it will result to a local minimizer of stuff like that. But using this general result, this is a very general result. These conditions, like, we do not per se assume very strict conditions. Even in this case, we are able to prove this particular result. So using this, we will be looking at uh, like some other algorithms where using this we can prove optimality results which we can know, which we usually know. So yeah, this is a general result regarding line search methods. So now we'll look at steepest descent method. So this is basically the gradient descent. In this case, our descent direction is the steepest descent itself. So the result that goes on with steepest descent method is, uh, suppose f from Rn to R is twice continuously differentiable, and that the iterates generated by steepest descent method with the exact line search method. So our optimization method is the steepest descent method with exact line search method. Given these two, then our iterates converges q linearly to a point x star where the Hessian matrix at that point is positive definite. This is one thing. And then this inequality is also satisfied for each point f of xk. This thing is satisfied. So if you see, basically this thing, this is a constant. These things are these lambdas are the eigenvalues of Hessian matrix at x star. So this is a constant, say some k, some r. So if you see, this can actually be seen as this rightly fits to the definition of q linear convergence. So here f of xk will converge to f of x star, and the rate of convergence is q linear, and the rate itself is this quantity. So that is one thing. And essentially, gradient descent will converge q linearly to a point where the Hessian matrix is Hessian matrix is positive definite. So here, one thing you should note, like when we have Hessian matrix positive definite, you might be saying that, yeah, this might be a strict local minimizer, but it might not be. Here we do not say that here from this we can tell that f of limit f of xk as k tends to infinity will be equal to f of x star, but we do not know if f of x star itself is 0. The gradient at this point is 0 or not, we do not know. So yeah, steepest descent doesn't guarantee us like it doesn't guarantee a local minimizer per se, but it does get to a point which is a decent solution, and the rate of convergence is q linear. Yeah. And then we have Newton's method. So in this Newton's method, essentially our descent direction is Hessian inverse at that point times the gradient at that point. So this is a vector and this is a matrix minus of that. So you take Hessian inverse. So basically what you do is you solve the linear system. Hessian times the step direction is equal to gradient. You solve that linear system at each point, and the solution of that will be your descent direction. That is a Newton's method, and the convergence result here, what it says is, if you have a twice differentiable function and that Hessian is ellipsis continuous in a neighborhood of x star. So here x star is a point where second order sufficient conditions hold. That is, x star is like strict local minimizer. So here, one thing I should note, the ellipsis continuous continuity of Hessian will just mean this. In place of gradient function, just replace it with Hessian, and we should have some constant L such that this will hold for all points in the neighborhood that we are considering. If that is satisfied, then we say Hessian function is a ellipsis continuous in that neighborhood. So here for this theorem, what we want is we want it to be ellipsis continuous in a neighborhood of x star where second order sufficient conditions hold. So given this, then consider an iteration of this form. So this is here we directly take the step length to be 1. We do not like restrict it to like we do not want to just take fractions of this. So we just take the whole step itself. And given this to be our Newton iteration updating step, then the results that we have is if the starting point x naught is sufficiently close to x star, the sequence of iterates converges to x star. So this is one important thing that you should note, that only if the starting point is very close to a strict local minimizer, only then the sequence converges to the local minimizer, strict local minimizer. In other cases, we cannot guarantee that. Okay, so this is where this thing comes, like the selecting of initial point. This is the case why it's non-trivial. Like for general, in general case, we cannot definitely say which point to choose. If we are lucky and if it's close to strict local minimizer, only then it converges to the minimizer. So this is one thing, and then the rate of convergence of the sequence of iterations that we generate is q quadratic. So since it converges to x star, the rate of convergence is q quadratic. So it rapidly converges to xk, and the sequence of gradient norms. Okay, this should have been norm. So the sequence of gradient norms converges again q quadratically to 0 this time. So actually here, since it converges to a strict local minimizer, so we have these two conditions that first of all it converges q quadratically to the strict local minimizer whenever it is the starting point is sufficiently close to x star, and the gradient norm, the sequence of gradient norm also converges with the same rate to 0. So this is about the Newton's method. So essentially, like if you now look at yeah, line search methods, first of all, in some cases, picking the initial point itself will be a very important thing. But
Uh, Jayadev, your voice has cut off. I'm not sure what the issue is. Okay, looks like it's disconnected. Let's just wait for a moment. Okay, so he has lost his internet connection. We'll wait for a minute, and if he's like, I'll just confirm with him. If he's not able to join, like, we'll conclude and have doubts later on. Okay, so he won't be able to join back. Yeah, it's not getting his internet back anytime soon. So yeah, we'll conclude the meet. And if you have any questions, like we can continue discussions on Discord. Yeah, this was very unexpected. I think, yeah, it's in Hyderabad. It's raining heavily, so yeah, we'll just continue discussions on Discord. So if you had any questions from the meet, please ask them in the Seminar Saturdays channel. I also have a few questions which I will be asking them. So yeah, thanks everyone for attending.